So bear with me as I'm trying to go through. Just to give more background about exponential functions, these were the notes that we would have done in class, along with other activities and things of that nature to go over exponential functions. But since people have expressed that they're struggling with the Odyssey-ware and that's our only option right now, I've decided to go through and show you the notes and give you some more background about them. So this would be the cover page, as you can tell. The number of cell divisions versus the number of cells, they're growing exponentially. The best way that I can explain it is also just if you're doubling a number every day, it's going from 2, 4, 8, 16, 32, 64, 128. It's getting very large in a very short amount of time. Another example is what's going on in the world right now with the pandemic, with the coronavirus, with COVID-19, is the numbers are growing exponentially. As one person affects 3 people, those people affect 3 more people, and the numbers just grow at an exponential rate. So this would have been the cover, exponential and logarithmic functions. Today I'm going to focus on exponential growth and decay, as long as the video allows me to. So whenever you go through, this here is the basic form of all exponential functions. And I also posted a blank one to the Google Classroom. You can use that, you can print it out, you can just look at it. It doesn't make a difference to me, but I just want to share the resources with you. Where B is the base, and bear with me because this is the first time that I've actually used this application. So B is the base. Again, bear with me because I've never used my stylus before. It's a new stylus. And it's a positive number other than 1. Doesn't make sense to have 1 to any power because we know 1 to any exponent is going to be still 1. So that doesn't make any sense. H is going to translate the graph horizontally. And I'm just going to abbreviate that. And what I mean by that is left and right, where K is going to translate the graph up and down. Guess what? H and K mean the same exact thing that they did when we had parabolas. Notice it's still a minus there in the form that we already circled because it's the exact same thing. So 2 to the x minus 3 power means it's going to go to the right. Guess what number? 3. Where do we think the x plus 2 is going to shift it? Not to the right, but to the left too. Same thing as parabolas and absolute value functions, cubic functions, quartic functions. Same thing. For this example here, where do you think the plus 1's going to move it? Wow, up 1. And the minus 7 is going to bump it down 7. So that's just staying the same. If A is positive, the graph is going to open up. And if A is negative, the graph is going to open down. And I can change, be reflected across the other axis as well, and we'll talk more about that later. So first thing, we're going to break it down and do 2 to the x power. I'm going to make it really simple, and we're going to stick to an xy table. And again, bear with me because this is the first time that I've used this stylus. I'm going to go from -3, -2, -1, throwing it back to an xy table. 0, 1, 2, 3, and let's do 4 just for the sake of 4. When you take 2 to the -3rd power, you get, hey, just to remind you, negative exponents turn things into fractions. So it's 1 over 2 times 2 times 2, which is 8. 2 to the -2nd power, guess what, is 1 over 2 times 2 is 4. It's supposed to be a 4. -1 is 1 over 2. What is 2 to the 0 power? Guess what? Any base to the 0 power is not equal to 0. It is equal to 1. And we talked about in class why that happens. So 2 to the 0 power is 1. What is 2 to the 1st power? 2. 2 squared, hopefully you know, is 4. 2 to the 3rd is 8. 2 to the 4th is 16, which obviously we're not going to be able to plot, but that's okay. It's a 16. So we go through and we plot our points. We go to -3, 1/8, and again, bear with me. Negative 2 to 1/4 kind of looks the same. Negative 1 to 1/2. 0 to 1. 1 to 2. And 2 to 4. And you plot those points. 3 to 8. And you plot those points. And then we're going to try to sketch our graph. This nice, and that looks horrible, but hopefully you get the gist. This nice exponential curve going through there. What you probably notice is you're like, wow, it looks like it's getting close to the x-axis. Hopefully you see that, and we're going to name that in a minute. So, whenever we go through the y-intercept, guess what? The y-intercept is always defined by when the x value is 0. Always, 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 always. At 0, for x in the table, the y value is 1. And guess what? It makes sense because that's where it's intersecting the y-axis. The domain, we look, are there any restrictions for the x value of the domain? No. We can plug any number in for x. It doesn't matter. So we're going to make it all real numbers. So we're throwing it back. Negative infinity to positive infinity. The range. Well, when you look at the table, y's values are going to really small. They look like they're getting close to 0. But is there any number that we can plug in for x that would make our y value 0 or negative? No. So for our range, and notice I'm using a parenthesis because I'm not including 0. Plug this in the Desmos. Look at the xy table. It's going to get really, really, really close to 0, but it's not going to reach 0. And that is called an asymptote, which is what we'll talk about in a minute. So as x approaches positive infinity, as x gets bigger, guess what? F of x or y is also going to positive infinity. As x is getting smaller, the function itself is going to 0. At the bottom, get to this one in a minute. It might skip this one actually, the second one, just for time purposes. The line, this imaginary green dashed line over here, y is equal to 0, is called an asymptote. So that is what Odyssey Ware is referring to when it talks about an asymptote, if you didn't read the notes. An asymptote is an imaginary line. So the same word goes right here. And again, bear with me. My handwriting is always bad, but it's worse on this. If my pen works. So an asymptote is a line that the graph approaches but will never touch. There are both horizontal and vertical asymptotes. We really won't get to vertical asymptotes until we see logarithmic functions. You can always work at your own pace for Odyssey Ware. You can finish it in June, like by June 3rd or the last day of school, or you can finish it in 2 weeks. But for graph 1, the asymptote is y is equal to 0 because a horizontal line is defined by y and it looks like it's getting closer to 0. And we'll talk about more as to why that's happening. I'm going to try to skip through some examples so that way I can get to other things that are more pertinent. Some of the questions in Odyssey Ware are a little bit extensive. Sorry about that. As far as what they're going through and having you do, it's really nothing more than I can say, but it can be pretty extensive. So there is a real-world exponential section, which is actually really neat. So just to talk about this, and it's talking about when a real-life quantity is growing by a fixed percent during a time period, can be modeled by this equation, where A would be represent. Oops, sorry about that. The original value, and again, I apologize for my handwriting. Oh God, this stupid thing. R is the rate of growth. Typically, it's as a percent, but we're going to make it into a decimal. T is the time, typically in years. Depends on the situation. And R plus 1 is the growth factor. That's decimal. How do we get a percent to a decimal? hopefully you remember, you take a percent and you divide it by 100, and that's how you get it to be a decimal. So hopefully you remember that. And rather than doing the graph right now, because I'm very certain you can plot points, I'm going to skip to these questions at the bottom. It says in 1970 the population was 330,000. In that 30-year time period, it's growing at a rate of 2.4%. Write the exponential growth model and how many people lived in the county in 1990. So if we're writing the growth model, since it gives us P, we'll use P rather than Y. We always take the original amount, which as you look in the problem, is right here. So we're going to take 330,000 and we're going to slap it right there. It's growing, so we're going to put 1 plus, and we're going to write 2.4 as a decimal, divided by 100, and you should get 1.024. And we know that we're going to take that to the power of t, and t is the amount of time. So if you're asked to figure out the population in 1990, all you would do is you'd be like, well, 1990 is 20 years later, so you would just plug in 20. Add 1 plus 0.24, take it to the 20th power in a calculator, multiply by the 330,000 at the end, and you get your answer. Same thing as down here. It says, what would the predicted current population be if York is growing? You're going to take the population. You always take the original. You take 1, since it's growing, it's going to be a plus. If it's decaying, getting smaller, you make it a minus. You put 0.5% as a decimal, if my stupid pen works. And you're going to look, and you're going to say, okay, current population from 1990 until now, that's 30 years. Crazy that it's 30 years. But you plug in 30. You add, use the exponent, and then you multiply by 40,000. We've got to save the compound interest for another day. Just sort of checking on my time here. And what I'll try to do is post the completed notes so that way you can see them. And I'll put this stuff here. But just in terms of graphing, since I know that's where most people actually are, I'm going to roll through this page very easily because hopefully after this you'll start seeing a gist. Whenever I look at all of these, first things first, the negatives, and let me grab a highlighter just to show this, but the ones that have a negative, well, guess what? I assume, just like normal, those graphs are likely going to be opening down. So that tells me that that's probably going to be D, B, and C. And guess what it is? So that works the same way as normal. As before, if it was 2, 3, 4, 5 being multiplied with A, it's going to make the graph a little bit more narrower. Whereas 1/2 is going to make it a little bit more gradual. Also, if we take 3 to the 0 power, guess what? Anything to the 0 power is 1. That tells me F is going through 0, 1. So I would say this is F. When I look between A and E, 4, 3, and 4, if 3 is going to be more steep, I assume that's A. Whereas if 4 is going to be more gradual, I'm going to assume that is E. And we're right. Same thing for the ones open now. So I'm going to let you do that yourself. And then again, I'm going to try to post the completed notes shortly so that way you get a gist of that. As we go through below, for every single one of these domains, we have no restriction for exponential functions with domain unless it's a real world example. Like if we're talking about the number of bacteria that exist, or the number of people infected by the COVID-19, 0 is our starting point. So that's where the domain would switch. But for all generic examples like these, the domain is going to be all real numbers. So you could literally put that for everything for the domain. The range will change. The y-intercept, all you're going to do is you're going to plug in 0 for x. Well, 3 to the 0 power is 1. So we know it's going to be at 0, 1. All of these will have an x value of 0. So you could already fill that in. And so on. The asymptote is what I'm going to talk about next. Whenever you look, your k value is going to help determine your asymptote, your range, and your end behavior. If you're not adding or subtracting on the outside, guess what? Your k value is technically 0. So here, the asymptote, we know it's exponential, it's going to be horizontal. It's y is equal to 0. The range, it's opening up, so from 0 to infinity. As x is going to go to positive infinity, it's keeping the same thing because it opens up. It's also going to go to positive infinity. And then when x goes to negative infinity, it's going to go to 0. Same thing down here. Whenever I go through for number 8 and I find the y-intercept, I plug in 0 for x. So I take 2 times 4 to 0 power. Well, 4 to the 0 power is 1. 2 times 1 is 2. Domain, we already talked about. Asymptote, k is 0. So it's going to be y is equal to 0. Range, guess what? Same thing as this. And behavior, same thing, because it opens up. Whenever you get to things like number 11, the only difference with the range is because it opens down, you would go from negative infinity to 0. That's literally the only difference. And as x is getting bigger, the y values are getting smaller. And it's still going to 0. Number 12 is where it gets a little bit different as far as the asymptote. Y-intercept, you do the same thing. You plug in 0 for x, you take 4 plus 3, and you get 7. So I'm just going to do that, so that way that's done. For the asymptote, it's exponential, so it's going to be a horizontal asymptote. K value, 3. Guess what? Y is 3. For the range, it opens up, so we're going to put 3 to infinity. And if you don't need to graph for any of these, but if you don't believe me, you can always check it, and you will see on Desmos that this is working out. So what I'm going to do is I'm going to end this video, which is on exponential growth. Hopefully in the next day or two I can do one on exponential decay, and hopefully I can get these notes posted for you, so that way you have something to go off of. So that's pretty much where we're at. Hopefully that helped explain it a little bit. These are one of my favorite things to talk about, so hopefully, I know honestly where isn't the best, but hopefully between the comp videos, going through this, looking at my notes, you're able to get a better understanding.